Hi, my name is John Fluker, and this is my Physics 2211 Lab 2 Motion of a Falling Object. For our first key concept, we have to know about Newton's second law, which says the net force on an object is the change in momentum over the change in time. This formula can be rewritten into the velocity update formula, which says V final equals V initial plus F net over m times delta t. The velocity update formula is also related to the position update formula, as RF equals R initial plus V average delta t. Next thing we'll talk about is gravity. The gravitational force equals the mass times the acceleration of gravity and points in the downwards direction. Near the Earth, it's approximately equal to g times m1 times m2 over the magnitude of r squared. You can rearrange this equation to find the acceleration of gravity, which equals 9.8 meters per second squared. Next, we'll talk about drag. Due to air particles, there is also a drag force that acts on objects. Drag force acts in the opposite direction of the force due to gravity, which will be upwards. The drag force gets larger over time until it reaches the same magnitude of the force of gravity. This is when an object reaches its terminal velocity. The drag force is modeled by B, which is a proportionally constant, times the magnitude of V squared. The purpose of this lab is to measure the position of a falling object that starts at rest through tracker. We'll then compare the motion to computational models done through growth slip. One model considers the forces of both gravity and drag, while the other considers just the force of gravity. Now we go into tracker and we can see the motion of our falling object. As we see it fall, we can see the y value change with respect to time. Now if we go into our computational models, for no drag, we can see that g equals 9.8 and our b is 0. For our equations, we have the velocity update formula, the position update formula, and the force of gravity. For our computational model with drag, we have g as 9.8, but now we have a proportionality constant. We solve the same velocity and position update formula, but now we also have a drag force counteracting the force of gravity. When we run the program for no drag, this is what we get. And for with drag, this is what we get. Now we compare our models. In orange, we have the computational model with no drag. In blue, we have the experimental model. And in gray, we have the computational model with drag. For our discussion, we can see that the computational model that considers drag force is closer to the experimental model than the computational model that doesn't. Possible errors could have been made in the placing of center of mass in tracker and a not completely accurate drag coefficient since it was calculated with trial and error. Which computational model predicts a terminal velocity? It's the one that considers the drag force. This can be seen in the right graph, where the velocity is approaching an asymptote, which would mean that the ball has a terminal velocity. Would the terminal velocity be the same if the object was thrown down with a force? Yes, however, the terminal velocity is reached quicker. As you can see in the code, we gave an initial velocity of -2, and we can see that the asymptote is reached quicker, but it's the same terminal velocity.